Hello, my name is Rudy, and I'll be talking to you guys about Pleiades. So Pleiades is basically an acronym for the following, and the only two words that you have to focus on are polynomial and event-based systems. So before even going into details of what Pleiades is, I should probably give a brief introduction of what event-based data are. So essentially, unlike RGB frames, which comes in like fixed timestamps, event-based are sort of just like very free-flowing spikes that just have almost you can consider them as continuous timestamps. So it is up to the user to basically bend them or put them into frames. So the problem is to fully capture the full temporal resolution of event-based data, we usually have like a very high sampling rate of the input frames. And naturally, given this input sampling rate, we'll have to use long temporal kernels. So if we were to just directly train long temporal kernels, it will be very unstable and you have a lot of parameters flowing around, which is not good. So one of the ideas that you can use this parameterization by orthogonal polynomials. And I'll briefly explain what is this later. So it's essentially instead of training each temporal kernel value one by one, you have this like alternative parameterization which compresses the space of trainable parameters. And if you're working with a continuous orthogonal polynomial, you can also have like this what we call the freely resample property. So you can take this polynomial for example, you can sample it very coarsely, or you can sample it like very finely. And this is obviously important for event-based data where the input sampling rate can change. So this is a very natural choice for handling event-based data. And third point is having this polynomial structure actually gives you this opportunity to do optimized computation. And I'm not going to go into too much detail here, but you can check out our sister work, Centaurus, and we talk about how, like, by this polynomial projection, you can come up with different orders of operation, and you can pick a optimal order for your input tensor size to optimize the compute. Okay, so here's a very simple, I guess, schematic of how you will build a temporal kernel from orthogonal polynomials. So what you see here, basically the orange like lines are visualization of a fixed orthogonal polynomial basis, and the green ones are the polynomial coefficients or the weighting. So you literally you just sum them up with this weighting factor and then you get a final temporal kernel. So it is very important to note that the line themselves or the curves are not actually trainable. The only trainable parts are the green coefficient. So here is a very trivial example where you have like 5 coefficients and then you have like, let's say 10 sampling points. So you can imagine this to be like a linear mapping from coefficients to temporal kernels. In this case, it's a R5 to R10 mapping. So instead of training 10 separate parameters, which is likely unstable, you only reduce this problem to training like 5. So this is like a very trivialized example in theory, or in practice you will probably come up with like 20 sample points or like even 100 sample points, in which case this becomes kind of important. So, and what is shown here is actually a very trivial sampling as well. It's just point-wise sampling. But in practice, you may want to have like trapezoid sampling and also like analytical integration to have more finer control of the continuous integration. Okay, so in the previous slide, we show you guys how to build temporal kernels from orthogonal polynomials, but actually it was a simplified example that only deals with one single channel. But all you guys know, like neural networks, they have different channels, especially CNNs. So actually the real picture is a bit more complex, but you can still visualize it somehow like this. So we first look at this, which is like the middle matrix, and that is a representation of the orthogonal polynomial discrete, sampled. And here on the left are the actual trainable matrix. So on the row you have channels, and on the columns you have coefficients. And essentially what this does is that for each channel you apply this coefficient weighting to sum up these orthogonal basis function, and in which case you get this like final matrix, which is just channels by discretized values. So essentially, like as I mentioned, it's like a linear mapping from trainable coefficients to the finally materialized, actualized temporal kernels values for each channel. And this is just one way of doing it. Like in this case, what we describe here is that you generate the temporal kernels first, and then maybe you can convolve them with the actual inputs, which is not shown here. But you can also have an alternative way of doing it is to reproject the inputs into coefficient space, and you actually convolve directly in that space. And this actually part of the Hippo paper, which is the origins of SSMs. So the two ways, so you may ask, okay, which way is better for us? And this is actually a very finer discussion we have in our sister work, Centaurus. And I recommend you to scan this QR code to check out our sister work. And there we'll talk about which is the optimal order of operation depending on your input feature size and your kernel feature size. Okay, so we just went over the core of the paper, which is to build temporal kernels from orthogonal polynomials. But there are actually also auxiliary details for the network that is also important in practice, especially for saving computations and memory. So the first design choice we made was to separate the temporal and temporal convolution blocks and the spatial convolution blocks. So you see here we have this like alternative structure where we do temporal convolution first and then followed by a spatial convolution, and then temporal convolution followed by another spatial convolution, and so on and so forth. So we just termed this like 1 plus 2D convnet, which I think is a pretty standard terminology used in the literature as well. And another design choice is that we make within each temporal block and spatial block, we configure it to be also depth-wise separable. So depth-wise separable is a concept introduced in MobileNet, which I encourage you guys to also check it out. So essentially, in traditional full convolution, we do this full channel plus spatial mixing. But if we do this depth-wise separable factorization, then you separate this spatial convolution part into this channel mixing part into 2 stages. And this essentially saves you a lot of computation and memory. So the third design choice we made was causal temporal convolution. So what causality means is that the current feature can only depend on past input from the previous layer. And this guarantee, basically, as soon as a new input comes in, you can just start processing immediately with the network and then come up with a prediction of the network that corresponds exactly to the current frame. And of course, I mean, this is very important for real-time processing. So that's why we decided to have this feature. And the final feature is the lightweight activation, which we just use Rudy because it's like simple and it's good for sparsity, and it's also good for like edge deployment because it doesn't involve any sort of complex floating point operations. Okay, so we just went over all the theory details of the network. So now we're just going to go over the empirical studies we did with Pleiades. So the first data set is the DVS 128 data set, and this is sort of considered to be the hello world of the event-based processing systems. And essentially what a data set is that you have event-based data of like a person doing different actions. So there's a hand gesture of like rolling your arms, and there's a hand gesture of like clapping your arms and so on and so forth. So the important thing to note here is that you check out the Pleiades performance with a majority filtering. It actually achieves like 100% test accuracy. So it completely just solves the data set, like trivializing it. So this is like a pretty major milestone because I don't think we've ever seen a data set just being solved in neural network processing. And the parameters are also pretty cheap, like it's comparable to some of the lighter ones. And of course, the max per second is also pretty cheap. So I think, this is a pretty good evidence that Pleiades supports like both performance and also like efficiency. Okay, so the curves you're seeing here actually comes from the previous data set as well, DVS 128. I guess the axes themselves are not really important, but let me just explain what they are. So the axis is latency, and the y-axis is accuracy. And essentially what latency is defined is how much data the network has seen before making an actual prediction. So naturally, I think the network has like a total receptive field of 600 milliseconds. So that's why you see the performance peaks out at around this point. So anything before that can be considered a form of early prediction, which is important for low latency systems. But actually the main theme I want to show is actually like you see how well these curves sort of overlaps, and what each curve represents is actually like an instance of a network with different temporal sampling rate. So let's say the base here is a sampling rate of 10 milliseconds. But as we mentioned before, because the underlying structure is a continuous polynomial, you can choose a step size to be a finer step size. So let's say I want like a coarser step size. In this case, I can use this orange 20 millisecond step size, or I want a finer step size, in which case I use this like green 5 millisecond step size. So in this case, you see no matter what step size you use, the temporal kernel basically kind of overlaps, or they're very close. So, and the one thing to note here is that we do not do any additional fine-tuning after resampling. We basically only do the resampling analytically, let's say via like a different integration window. So this is like I think a pretty cool stuff to show, because it implies that once you train a Pleiades network for a given sampling rate, you can actually just resample it on the fly during inference without any sort of fine-tuning cost. And here is another dataset we recently did for CVPR AI for Streaming 2024, and this essentially is pupil tracking. So here's an event, representation of a pupil, and then the goal is to basically mark the location of the pupil. So here we also did Pleiades with CenterNet, and essentially I think we outperform everybody on all categories with a significantly fewer parameters. And here, I think this is the holy grail of event-based vision, which is, I think, to my knowledge, one of the largest data set for event-based processing. And this is by using the Prophecy 1 megapixel event camera they call it a Gen 4 data set. So essentially, you have, I think, 14 hours of recordings of event-based road scene data. And the task here is object detection of cars, pedestrians, bicycle, stop signs, and other road scene stuff. And here you see Pleiades actually outperforms the nearest competitor by quite a bit, actually, and with a significantly fewer parameters and significantly fewer max per second, and also with a much higher FPS. And this is actually configurable, so this can be as high as you want. So thanks for listening to my talk, and I encourage you to check out Pleiades. So the QR code for the paper and the QR code for the code are both shown on the screen. So feel free to just scan it, and it will take you to the page.